Hi guys, it's Mrs. Discavich. I have a little video for you today about ionic bonds as we do bonding and nomenclature. So let's get going here. First off, we want to know, and of course you guys ask me this, why do we work so hard on electron arrangement? Who really cares, Mrs. D? Well, actually, it does make a big difference as to how we make the bonds as to where the electrons are. Those electrons that are valence electrons, they're out there doing the work. They're the little worker bees of the atom itself. So we need to make sure we know what's going on with those. Chemical properties of an element depend on three things. The first thing is the number of valence electrons. So those valence electrons are important. It is important to know how many are out there doing the job and how many can be taken and how many are actually needed to have a full outer shell to make a stable compound, stable atoms. Second thing is the energy levels of valence electrons. So if you remember on the periodic table, looking at the periods for the periodic table, basically there's energy levels 1 through 7. Remember, D energy level is 3D, 4D, 5D, and 6D, and F's are 4F and 5F. The 7 energy level only contains S and P. So you guys remember that just by looking at your periodic table. The third thing is the size of the atom. The size of the atom is also important because we have, as we were looking at the atomic radius, it depends on, hey, are those electrons, like how close are they to the nucleus? What kind of, are we going to have a single bond, a double bond, a triple bond? So that makes a big difference with the size of the atom as well. So these three things, they do help determine the kind of chemical bonds and how many chemical bonds can be formed by an atom. First of all, with ionic compounds, we want to make sure we get the term ionic compounds because we have a combination of negative and positive ions. So those positive ions come from metals. And those metals are located, if you look at the table below, toward the left. They're the light blue in color. Notice the representative elements are the only ones that are showing it right now. That doesn't mean transition metals can't be part of a compound. They certainly can. The nonmetals then are in the yellow, and they make the negative ions or anions. And those anions like to bond with the cations, and they are able to form an attraction. Now, this attraction, we have to understand, is not like a force. So I know that you've done some forces in physics and physical science and stuff like that. There's a difference between a sense of attraction, holding them together as a bond, compared to a force. And this is definitely just an attraction because of the positive and negative there. Ionic compounds, their oppositely charged ions are held together by these opposite electrical charges. So just like magnets repel whenever you're playing with magnets or anything, if you have two atoms that typically make anions, which would be like two nonmetals, they're not going to ionically bond. There's not that sense of attraction there. But if you have, like we have here, we have sodium, we have chlorine. Sodium makes a positively charged cation. Chlorine makes an anion. So of course, they're going to be attracted to one another. If you look there at the bottom, it says ionic ions are held together by an ionic bond. We typically say ionic bonds, but there are some texts that refer to these bonds as electrocovalent bonds. I personally do not call them electrocovalent bonds just because covalent bonds, I don't want you to get them confused with a covalent bond, which actually shares instead of takes. So what is happening when an ionic bond forms? And so I'm going to draw some pictures here, and let me get a good color on my pen. And so what we have here, we have sodium and chlorine. And so it's good for us to know the Lewis structures when we're playing with sodium and chlorine. So we know, based from our periodic table, looking at the representative elements, sodium has 1 valence electron, while chlorine has 7 valence electrons. So what's going to happen here is the obvious. Chlorine is going to take that 1 valence electron from sodium. Now notice I said take. Sodium's not like, oh, let me give you my electron. Chlorine's like, give me all your electrons right now. That's more so how the whole situation works. So once sodium has to give chlorine its electron, sodium becomes a positive or a cation, and chlorine becomes a negative or an anion. If you add +1 to -1, you get an overall charge of 0. Now, when I put this together, I say, okay, well, I have one sodium and one chlorine. Which one do I write first? And there is an important thing to remember when you do this. When you write compounds, your metal goes first. If you have a metal in your compound, your metal always goes first. So I can write the compound as NaCl because I have an Na and I have a Cl, and there's just one of each. Now, the second thing, I have magnesium, and magnesium has 2 valence electrons. And I also have fluorine, and fluorine has 7 valence electrons. So one would think, wait, there's 2 and it only needs 1. But what happens is this fluorine takes a valence electron from magnesium. It becomes an anion. And then we have more fluorines in there because really atoms are rarely ever by themselves unless we're doing crazy experiments on them. So this fluorine is going to take an electron from magnesium. Magnesium lost 2 electrons, so it becomes a 2 plus, and fluorine, both of them become a minus. So if we add this, we have 2 plus -1, an overall charge of 0. So we have 1 magnesium, 2 fluorines. Remember, we always put our metal first, so magnesium goes first, so we have MgF2. On to the next one. What about calcium and nitrogen? Calcium and nitrogen is a little bit different because calcium has 2 valence electrons, where nitrogen has 5 valence electrons. So this is going to end up being a little bit different. So nitrogen is going to take calcium's valence electrons, and calcium lost both electrons, both valence, so it becomes a 2 plus. Well, of course, there's more calcium electrons hanging, or calcium atoms hanging out in there. So this nitrogen is going to take this one from the calcium. The nitrogen is then full as it's gained 3 electrons, so it becomes a 3 minus charge. But what happens here is calcium has an extra electron that's going to be taken. And so nitrogen is going to do that job, and nitrogen has 5 valence electrons to start. Nitrogen takes that calcium. Calcium then becomes a 2 plus cation because it lost 2 electrons. And nitrogen says, hey, I could use 2 more electrons. And so it goes and finds another calcium. And so once it finds another calcium, it takes this calcium's valence electrons. And now we're finally evened out where nitrogen has gained 3, calcium lost its 2, and we have no more electrons that aren't taken and no more spaces that aren't used. So we have 2 plus, 2 plus, 2 plus, so we have 6 minus 3 minus 3, an overall charge of 0. And that's what we're looking for in a compound. Now, count how many CAs we have. 1, 2, 3, and 2 nitrogens. Remember, we're going to always write the metal first. So we have 3 calciums, 2 nitrogens. So I get Ca3N2. So I like this little meme here. It says the name's bond, ionic bond, taken, not shared. So if you've ever watched James Bond movies, he always says shaken, not stirred when he's talking about his cocktails. So anyway, taken, not shared, the electrons are taken, not shared, compared to with covalent bonds, we will find that those electrons are in fact shared. So which of the following sets could make an ionic compound? So let's take a look here. We have a K plus and an F minus. So since we have a cation and an anion, yes, this should in fact make an ionic compound. We have a cation and a cation. No, we're not going to make an ionic compound. They don't want to be around each other. We have an anion and an anion. So no, we don't want, they're going to repel. They're 2 anions or 2 negatives. And then finally, again, we have a cation and an anion. So of course, this will make an ionic bond as well. The goal of the ion is to have achieved this electron configuration like a noble gas. So remember that octet rule. Octet means 8. These ions are held together by their opposite electric charges. So again, it's more of an attraction and not a force. So let's look at number 1 here. The metallic ion is K plus or F minus. Well, our metal is always going to be the electron donor. So K plus. You can also tell that from where it's located on the periodic table. The nonmetallic ion is F minus. So fluorine is definitely a nonmetal on the periodic table. So the K plus ion has the same number of electrons as which noble gas atom? So if you look at your periodic table, K plus, K typically has 19 electrons. And if we make a cation and lose one, we'll now have 18 electrons. Well, what noble gas has 18 electrons? Good old argon. And then the F minus ion has the number of electrons as which noble gas? Well, typically an F has 9 electrons. And if it becomes F minus, it now has 10 electrons. And 10 electrons is also the same as neon. So again, those are isoelectronic. Remember that term from earlier we've talked about a lot, isoelectronic. When an ion has the same electron configuration as a noble gas. So writing the formula for an ionic compound, again, we always write the most metallic element first. But which of the following are written correctly? So all we have to do is check, is magnesium the metal in this compound? Yes, so that's written correctly. Lithium is the metal. Yes. Potassium's the metal and it's written second. No, this is not okay. And calcium's the metal and it's written second. And no, that's not okay. What if our ions have charges that don't equal? For example, if we say we want to make an ionic compound with calcium 2 plus and chlorine 1 minus ions. So another way we can do this, we can draw this out. And we can also, I want you to learn how to draw it out, but I want you to also know how to do this, where calcium is on the periodic table where it typically makes a 2 plus cation when it loses its electrons, where chlorine makes a 1 minus anion. So we can do good old crisscross applesauce where we bring the numbers down. So this 1 goes right here and the 2 here. Thus we get CaCl2. Now, if we were to draw that out, we would see that Ca and chlorine then has 7 valence electrons. So chlorine is going to take 1 from calcium, become an anion. We'd have another chlorine down here. Chlorine will take another 1 from calcium, become an anion, and calcium becomes a 2 plus cation. So we have 2 plus minus 1 equals 0. So instead of having to draw all of these every single time, we can simply look at what charges will they typically make and crisscross. So we have CaCl2. That means for every 1 calcium, we are going to have 2 chlorines. So here's another practice here with a compound made up of the ions Mg2 plus and Br minus. So we have Mg typically makes a 2 plus. Br typically makes a minus 1. If we crisscross, then we have MgBr2. We could draw that out and get the same thing, but what you need to understand is for every 1 magnesium, there are 2 bromines to make this compound. Finally, we have sodium and we have sulfur. So again, we have sodium. If you look at the periodic table, sodium typically makes a +1 charge. Sulfur typically makes a 2 minus charge. So if we crisscross, we're going to have Na2S. That means we'll have 2 sodiums for every 1 S in our compound. And finally, here's another one with calcium and phosphorus. Calcium typically makes a 2 plus. Phosphorus typically makes a 3 minus. We could draw it out, have a whole bunch of drawings, a whole bunch of arrows, or we could crisscross and we'd have Ca3P2 for calcium phosphide. So, guys, this is just a good start for ionic compounds. And if you have questions, make sure you ask. But keep going with these videos, and you will pull together all of this fun with ionic compounds because we know it's fun, right? Have a good day.